Let's see another example of the central limit theorem for um, categories, okay, or also known as the normal approximation to the binomial distribution. Okay, so here you assume a die is fair and you toss it 200 times. Okay, so the percentage of sixes that come up is going to be observed. What actually happened, out of the 200 times, we got 45 of those 200 times that it came up as a 6. Okay, so does this indicate the die is fair? So here, the number of times we sampled is 200. The probability of getting a 6, or p, or the proportion, is 1 over 6. Okay, so if it's fair, then p equals 0.16 repeat. Okay, here, what we actually found from our sample was 45 out of the 200. This is the proportion, the sample proportion of successes. Okay, so here you could talk about y, the number of successes is 45, or you can talk about p hat. So there are 3 different scales you can talk about. The proportion scale, okay, sort of like percentages or decimals, the number of successes, which is y, or the z-score. Okay, so here, then the middle, we expect to see 1/6 amount of, doesn't matter what the sample size is, 1/6 of the sample size we expect to be sixes. Here in this case, we actually have, out of the 200 times we tried, we expect every 6th one to be a 6, so 200 divided by 6. The number of successes that we expected is 33.3 repeater, so we expect 33.3 times out of 200 to get a 6. And then in terms of a z-score, this is the middle, so the z-score will be 0. Okay, so what we actually got, the sample that we got, was 45 out of 200. Okay, so this is the proportion, so 45 out of 200 will get a decimal. The number of successes would be 45, and then the z-score here, this is going to be 45 divided by 200, subtract p, which is the middle, all over p times 1 minus p divided by n, and I'll take the square root. Okay, so here the z-score for this particular situation is 2.21. Okay, so here this is the z-score. If you're using the z-table then, you can go to the row 2.2 and the column 0.01 and find this area. This is 98.64%. So this area here, from this point all the way over here, the likelihood of being there is 98.64%. 1 minus that, this area out here, is then somewhere around 1%. So 1 minus 98.64 happens to be 0.0136. Okay, so then the question here is, did we get a rare sample? And because this is so small, this is 1%, the answer is yes, we got a very, very, very rare sample. Okay, so there's 2 possibilities. Either our die is not fair, and that explains why we got so many 6s, or our die is fair, and we just happen to see a very rare case. Okay, so here, if the probability is fair, then the chance of getting 45 or more 6s is only 1% chance. Okay, so again, you start to look at this probability and start to decide which of these 2 possibilities seems more likely. Okay, so if we're only talking about a 1% chance that this actually would happen, what do you believe? Do you believe that the die is fair and we just got very, very lucky to see that? Or do you believe maybe the die is not fair and that's why we saw more 6s? Okay, the reason, of course, so that's the end of this question, but the reason that it's called the binomial, the normal approximation to the binomial, is that here we've used the normal distribution to talk about this, but in truth we could have also used the binomial. So actually this situation is really binomial, where we've got 200 tries and the probability of success is 1/6. We're looking for the probability that y is greater than or equal to 45, which can be calculated by just doing 1 minus the probability of less than or equal to 44. Here, when you do it as an actual binomial, you get the value 0.0198. Okay, it's not the exact same. As we said, this is the normal approximation to the binomial. Okay, so here the central limit theorem is suggesting that the proportion is about 0.0136, and the exact probability is actually 0.0198. So there's a little bit of difference here. It is an approximate, but the central limit theorem does work. Here, the larger and larger n is, okay, so here we've rolled 200 times, but the larger and larger that n is, the better and better the normal distribution will do. So the closer these two values will get to each other.